Alright class, in this video we're going to talk about logarithms and log properties. So I'm going to talk fast, so pause it as you feel needed. So the definition of a log base a of x equals y, if and only if a to the y equals x. So that means if we're trying to calculate a log, what's the log base 2 of 32? Okay, well that means 2 to the question mark equals 32. So you just have to figure out what do I raise 32, what do I raise 2 to get 32, and the answer is 5. So 2 to the 5th equals 32. 32, not 36. So log base 2 of 32 equals 5. Okay? Not that you're going to be doing too much of that, but that's, you know, the sort of the definition. There are two special logs. Okay. Log base 10 of x is written as log of x, and the 10 is supposed to be understood. That's called a common log. Okay, your decibel scale is based on log base 10. So then a log base e, where e is the natural number, that's equal to the natural log, that's ln not in, okay? And then let's see, what else should we talk about before we get into the nitty-gritty? The inverse property. So when you solve equations, you're going to need this. So logs and exponential functions are inverses, so that means log base a of a to the x is x. Okay, that works in reverse. So a to the log base a of x is also x. Okay, with some extra little things we'll have to worry about when we get to equations, and we'll worry about that later. Okay, properties of logs. There are three main properties. Of course, I could write it. Maybe I should write it down over here. We know that log base a of 1 is 0, because a to the 0 would be 1. Okay, for any base a, it doesn't really matter what the base is. So that's another thing to note. Properties of logs. Okay, so I'm going to actually prove one of these. So log base a of x times y is log base a of x plus log base a of y. Okay, there's the second one. Log base a of x raised to the r power would be r times log base a of x. And the third one, log base a of x over y is log base a of x minus log base a of y. Okay, and those properties can be proved in succession. You can use property 1 to prove property 2, and then if you had a negative exponent, negative 1, for example, for property 2, you could use that for property 3. So I'm going to prove property 1. Okay, so how am I going to do that? I'm going to say that log base a of little x is capital X. Log base a of little y is capital Y. And log base a of xy is capital Z. Okay, so why would I do that? We would use how log is defined as a definition and rewrite that in exponential form. So this means a to the capital X is little x, a to the capital Y is little y, and a to the capital Z would be xy. Okay? Alright, then if we take these first two things, x times y would be a to the x times a to the y, but also x times y is a to the z. because we made that assumption. And then if we just use exponential properties, we get our result. A to the x plus y, the pen's run out of ink here, equals a to the z, and we would see then that x plus y equals z, and we fill that out with what x, y, and z are equal to, and we get that log base a of little x plus log base a of little y equals log base a of xy. And there you go, there's your proof. Okay, so how would you use these? You would use those properties to go backwards and forwards. Okay, so for example, we're going to expand and contract logarithms with those properties. So let me write my example down. Okay, so we're going to write the following as a single logarithm. Okay, so how are we going to do that? So we're going to use property 2 in reverse. We know that r log base a of x is log base a of x to the r. So this is going to be log base 3 of x minus log base 3 of y plus log base 3 of z to the fourth. Okay, so you need to get the coefficients raised to powers first. And then we just, everything with a plus goes in the numerator and everything with a minus goes in the denominator. So I don't know if you can hear that motorcycle, but they need a muffler. That's x, z to the fourth. Those are both things that belong in the numerator because they have plus signs in front of it. And then log base 3 of y goes in the bottom. Okay, so that would be to contract a logarithm. And you need that to be able to solve equations. Okay, so we also want to expand a logarithm. Okay, so how do we do that? We do the same process just in reverse. Okay, so I have three terms. There's one in the denominator, two are in the numerator. So I'm going to write it like this. So this is natural log of x plus the natural log of the cube root of x minus 1 minus because that one's in the denominator, the natural log of x plus 2 squared. Okay, and then we're going to pull our exponents down. I don't have any for the first term, but the exponent here, this is cube root, so it's raised to the 1/3. So this would be plus 1/3 natural log x minus 1, that one's squared, so minus 2 natural log, I need to move this up some, don't I? Natural log of x plus 2. Okay, so that's what it looks like when they ask you to expand versus contract. You're going to need this for something called logarithmic differentiation, which is the derivative of a really complicated term that you trick it with logs first and make it a little easier.